Leave a glass of milk on a warm counter or drop a clean iron nail into wet mud, and you are watching matter in a state of constant, chaotic transition. These shifts are often subtle. You can see it as grapes ferment into wine, or feel it during the invisible exchange of gases every time you take a breath. In every one of these instances, the original substance is gone. Its chemical identity has been altered, resulting in a new material with entirely different properties. We can easily observe the before and the after of these objects. The challenge is developing a system to track exactly what happens in the invisible space between them. To see this transition clearly, we can isolate a single reaction. When a metallic magnesium ribbon is held with tongs and exposed to a flame, it ignites with a sudden, intense white light. The physical changes are immediate. The metal ribbon is replaced by a brittle white ash called magnesium oxide, accompanied by a sharp rise in temperature and a total shift in color. Describing this entire sequence, the state changes, the light, and the heat, requires long, detailed sentences. If we tried to document every reaction this way, the sheer volume of information would become unmanageable. To move forward, science uses a universal shorthand, a mathematical way to represent these physical transformations with total precision. We start by translating the experiment into a word equation. Magnesium plus oxygen yields magnesium oxide. We then condense that further into a skeletal chemical formula. Mg plus O2 produces MgO. This skeletal formula contains a logical error. On the left side, the oxygen molecule has 2 atoms. On the right, inside the magnesium oxide, there is only one. The law of conservation of mass states that matter cannot be created or destroyed. That second oxygen atom didn't simply vanish. It must be accounted for in the final product. We solve this using the hit and trial method. We multiply the molecules until both sides match. By doubling the magnesium on the left and the magnesium oxide on the right, the equation balances perfectly. This rule is absolute. Whether you are reacting iron with water or fuel with oxygen, every atom that enters the reaction must be visible in the output. Balancing equations confirms that every reaction follows a strict logic. It is a measurable reshuffling of atomic puzzle pieces, where nothing is lost and nothing is gained. Once you can read this language, the infinite variety of changes in the natural world begins to fall into a few recognizable patterns. In combination reactions, multiple elements merge into one. This is what happens when coal burns, as carbon and oxygen join to form carbon dioxide. Decomposition reactions do the opposite. When heat is applied to lead nitrate, the single compound breaks apart, releasing oxygen and the distinct brown fumes of nitrogen dioxide. In precipitation reactions, mixing 2 clear liquids forces an entirely new, insoluble solid to form and drop out of the solution. Finally, redox reactions involve the simultaneous gain and loss of oxygen. You can see this by heating copper powder until it pulls oxygen from the air and turns black. From the growth of a plant to the cooling of a star, these fundamental patterns dictate how matter interacts. These laboratory examples help us understand massive real-world events. That redox reaction is the same mechanism responsible for the corrosion eating away at steel bridges and ship hulls. This single chemical pattern causes billions of dollars in structural damage every year, as it slowly breaks down the materials we use to build our world. This is why we balance equations. It allows us to calculate exactly how materials will degrade over time, or how much energy a specific fuel will provide. By learning to identify and balance these reactions, we move from simply observing the world to understanding the specific mechanics that make physical change possible.